Okay, so welcome again to the Crypto Cafe. And today we have Tran, who is a graduate student here in the math department. And I think she was always interested in cryptography from the beginning. So she's been working with me and Shibai on some project for the post-quantum candidates until now. And then she's been to a few crypto schools, a few conferences, and now she's going to talk to us about the Mersenne-based crypto system, which is somewhat unusual in the panorama of all these lattice-based schemes and code-based schemes. So something a little bit different and based on number theory, a little bit more hands-on. So, Tran.
Yeah, thank you. So today we talk about a cryptography system based on Mersenne number. So actually, this system was first introduced by Divesh Aggarwal, Antoine Joux, Anupam Prakash, and Miklos Santha in 2017. But after like several weeks later, they have an attack on the system, and then they propose a new cryptography system to fix the reverse attack, and it is still safe until now. So as you guys know, we also have a list +1 cryptography submissions, and currently we have around seconds. The author of this cryptography system also submits a proposal to NIST, and there's a name Mersenne 756839, but it's only alive for rounds for the first round. For the second round it will not be chosen. So first, I want to say that this is a new cryptography system, and this belongs to the family of Antoine Joux and code-based cryptography system. In Antoine Joux, we use polynomial rings, but in this cryptography system, we use different rings. The rings based on Mersenne number. So let's make a quick overview about public key crypto system. So in a normal setup of public key cryptography system, we have four steps. The first step is first we need to generate something like a security parameter 1 to the k. The second process is we will generate a pair of public key and secret keys. So suppose that I want to send some information to someone that I know. I will use the public key to encrypt my message M, and then I obtain a ciphertext. I send this ciphertext to this person, and because this person they have their own secret key, they will use the secret key to decrypt again and obtain the message. So this is just a quick overview about public key crypto system. We will jump into Mersenne by crypto system. So let's fix some definition first. So let n be a prime number, and we set b equal to 2 to the n subtract with 1. A number b is called a Mersenne number if we have n is a prime, and then if b also itself is a prime number, then we call it Mersenne prime. For example, we have a first few Mersenne prime like 2 to the 2 subtract with 1, 2 to the 30 subtract with 1. Mersenne prime is generally in some cryptography system, they often use Mersenne number like for the pseudo RAM. But now the author of this paper, they want to construct a cryptography system based on the Mersenne RAM. The Mersenne RAM, they have a good property that If they have some good property about the Hemingway's property on a number based on the ring of z over b to the z, zb, which be a Mersenne graph. First, let we fix some definition about the Hemingway of a number. So suppose that we have some number x, and then we present x in a binary presentation, and then we will say that a Hemingway of x will be equal to the number of the big ones in this binary presentations, and we compute the Hemingway distance up to number equal to the different position up to binary presentations. Now we will work with the ring z over bz, which b is our Mersenne graph, and there are some property about the Hemingways of element belong to R, such that the Hemingways of x plus y always smaller than the Hemingway of x plus the Hemingway of y. So I mean, intuitively it's very easy to see, because for example, if I have this example here, we will see that when we make the summation of 1, this is gonna be equal to 0. We can prove that using the induction, and I think that is not very difficult to do. The second property that if we have element x belong to R, and then we rotation the binary representation, the number of the big one in this binary representation is just the same. The third property that if we have a product of two number, the Hamming of the product will be smaller than the product of its Hammings. And for the property 4 and 5, it's just induced from the property of binary representation. So if we have a number and then we rotate this number like a cycle, binary cycle rotation, the distance, the Hemingway distance will be the same. On this also apply for the sum. So we will need this kind of property for some proof later. So we start with the first proposal. Let me remind you a little bit. So in the first version of this paper, the author proposed a Mersenne cryptography system based on apply for only one bit. First we set up like we will work with the ring R, which B is a Mersenne prime, and we define H such that the set of all elements belong to the ring R, such that the Hemingway of this element always equal to x, which x is some small number. That means RH is just a set of low Hemingway elements of R. Okay, so we start with the key generation. First, we're gonna take some element R uniformly at random from the ring R, and then we take F and G low Hemingway element. Such that they also set up some condition for the constant for the Hemingway H, so that for h to the square smaller than n smaller than 16 x squared. And then we're gonna have the public key. Our public key will be equal to f divided by g, and our series key will be g. Here we should note that on the operation we work in the ring R. So, and then when I say that's f over g, that means it's just like a normal number, and then I take the operation over this is just the ring operation. Okay, so let's start with the encryption. So suppose that we want to encrypt a bit message. b, the small b. So b can be equal to 0 or 1. So we will choose A and B uniformly random with the condition that the Hamming weight of A and the Hamming weight of B will be equal to H. So that means A and B are elements of R such that they have a low Hamming weight. So the encryption will set up like C will be equal to -1 to the power of B times with a H plus B. And the decryption will set up like after we receive a ciphertext C, we will time it with G, and then we obtain a new expression. We will compute the Hamming weight of D. So if the value of D is very small, we will return B equal to 0, and if the value of D is very large, we will return B equal to 1. So why we have this condition? Because here you will see that because A, F, B, G is a low Hamming weight element. So that means that if B is 1, that means D will be the Hamming weight of AF will be like it will be okay. So let's start with B equal to 0. So that means the Hamming weight of A and F will be smaller than 2 times with the square of H, right? Do you have any questions so far? Okay. Let's take some toy example to see what's happened. Let's take B equal to 2 to the power of 13 subject with 1. And we choose something very simple. Our Hamming weight only equal to 1. Our random variable R will be equal to this one. We set F equal to 1, G also equal to 1024. Our public key equal to A, and our secret key will be equal to G 1024. And then we want to encrypt a big message B. First we will choose A equal to 16 and B equal to 32. So we compute the ciphertext C. The ciphertext C will be equal to 160 or -160. We just leave it alone here with and then for the decryption, we compute it again, and then we obtain like D will be equal to 20 or D equal to -20. And here we will see that for D equal to 20, that means B equal to 1. The Hamming weight of the big DSE will be very small. It will be equal to 2. And then if B equal to 1, that means D will be equal to -20. So and then we compute. We just change the -20 into the positive, and then we convert it into a binary representation, and then we compute the Hamming weight equal to 11. So we see that the security of this crypto system is based on assumption, and people call that the Mersenne low ratio assumptions. They say that suppose that we have two elements, and this element they have a low Hamming weight S, and then we compute H equal to F over G. The decisional problem is first suppose that we have 8. And we have another random variable that they were encoded as n bits. So can we distinguish between H and some random variable? The second problem is suppose that we have 8. How can we find F and G? So after the first So one of the easy way we want to do that, we will use, like a normal way we want to do that, we will use brute force to attack this assumption. So the brute force means that, so currently now we don't have anything, so we just make a guess. So we just guess the variable g. So because we know that f and g have a long Hamming weight and their Hamming weight equal to f. So that means we will try to guess on the possibility of g. And then after we have g, we have 8, we compute f again, and then we check if the f that we obtain satisfy the condition that the Hamming weight of f also equal to 8. So this is the first thing people think about, but it's not efficient. So after the first proposal of this of author Bernadette, Conley, Gerard, and Nakaches wrote both a latest attack on this scheme. Okay, so I will give you a idea about this attack. So suppose we have a trace of n bit. We know the value of 8. We want to find f and g. So the first thing I will do, like I will sample some random partition b and q. What does it mean? First of all, that we have some element like g, and then I encode it into binary representation. I have this binary representation. So a partition is just like we group consecutive of bits together. But we want to group it into somehow such that each group they will present because for example, if we have G is a long Hamming weight element, so that means the binary vector is very small. So if we just try to group they are small, that means they have a little bit of 1 in their binary representation. So they just try to group some partition that they can group some they can group a group of bit 1 together. First of all, that if I have C like this, I can partition is like 4 partitions on the screen, and then I will present I will compute a presentation of C by I take the last bit of each group. In this case, we are very lucky because we only have one bit 1 in each partition. So the presentation of C will be equal to 2, 0, 1, and 2. Okay, and then we can have the expression like G equal to the exactly binary presentation of G. So in the second step, Bernadette trying to construct a lattice. He has element 8. He converts 8 into actually he tried to sample some two random partitions B and Q. This is the partitions of actually this is the partitions of F and G, that the element F and G that we want to find. But we don't know exactly how we just sample random and then we put it into the lattice. So actually this is a presentation of F and this is a presentation of G. And then we have this lattice, This lattice have the property that the determinants of this lattice equal to n. And then they run a triple L algorithm on L to find an output vector. And this output vector, we hope that this output vector will contain information of f and g. Actually, we want to find some soft vector that satisfy the condition of triple L algorithm. So triple L algorithm is an algorithm that given a lattice, some constant gamma, we want to return a soft basis of this lattice such that the soft vector in this, the first soft vector in this basis satisfy two conditions. So the idea of Benedetto he tried to run the triple L algorithm to find the output vector, and this output vector is the first vector in the basis output from triple L algorithm. And then we hope that this one will be the presentation of f and this one is the presentation of g. But so after we obtain this vector, we will check the hand weight of f and g again. If they satisfy this condition, like the hand weight of f equal to the hand weight of g equal to 8, that means we're done. Because, yeah. And if we cannot success, they will repeat the procedure again until they can find satisfy an output vector satisfy our condition. And the complexity for this algorithm is the complexity for this algorithm, if I remember exactly, is gonna be nearly 2 to the power of 8, which 8 is a Hamming weight.
Do we repeat the procedure for different partitions?
For different partitions. Okay. So first,
do we repeat the procedure for different?
Yeah. I mean, they will repeat in the first step. They will sample another random partition,
okay,
and then they will repeat step by step until they find some suitable partition. Okay. So because of this attack, the group of authors they propose another scheme, and they say that the multi-bit Mersenne Cryptography system, we will keep the setup as the version of single bit, but for the second for the second system, we will also use some error encoding and decoding algorithm. We will talk about it later. So first, they will choose R from uniformly at random, F and G add two elements such that they have a low Hamming weight 8. And they compute the public key and the secret key like this. For the encryption, first they want to encrypt some message M. So they will sample some 3 elements A, B1 and B2 such that A, B1 and B2 they have a low Hamming weight. To encrypt a message M, they will compute a type of C1 and C2 such that C1 equal to AR plus B1 and C2 equal to AT plus B2, and then they will use the error encoding algorithm to encode the message M, and they saw this with the output from this summation. So the sort operation mean first we will compute like a normal element in the ring R, and then we transfer it into the binary representation, and then we solve with epsilon M, and then we convert it into integer again, element of R again. For the decryption, they will use the decoding algorithm. They will compute FC1 solved with C2 such that So we replace F, C1 and C2, and then we obtain this one. So from here, to obtain the original message M, we need to prove, we need to notice first thing that this one is low Hemingway. This one, the product, this product is they are low Hemingway, this also low Hemingway, so we can consider it like errors. And then, so our problem is we need to choose an error correcting code so that the probability to recover the message is high. Okay. They suppose us to choose a Ritzmuller curve or the repetition code. But let's see. First they prove that. So suppose we have UN be a random variable, and this random variable is uniformly on the ring R. So for every element S belong to H, and for every small epsilon, we're gonna have the probability, the Hamming distance between a random variable UN and UN plus is bigger than 2H times with 1 plus epsilon. This probability will be valid. So based on this theorem, first we're gonna see that this. Okay. So in our decryption process, we have two bars. The first bar is the epsilon m, and the second bar is the error. So first we prove that the Hamming distance of FR AR plus B1 and FAR, they are bounded. So we just apply the theorems, and then we have the first inequality. And we also apply the theorem again, and then we have the second inequality. So after that, because we know that if we back to the property, of the Hamming way, so we have the Hamming way of S plus Y will be always bounded by the summation of each Hamming way of X plus Hamming way of Y. So we just apply this triangle inequality, and then we obtain the second, the third inequality. So actually, we just need to know that because the Hamming distance of FRAR plus B1 and the Hamming distance of this one, they are bounded. So if we can choose some appropriate error correction code such that it corrects up to this constant, then the probability that we can recover the message M is 1 subtract with delta. With delta is some constant that we fix in the beginning. Okay, so this theorem guarantee us that if we can find some error correcting code, we can successfully recover the message M. So we're back to the security of this cryptography system. The first security of the single bit system based on the Mersenne ratio assumption. But the security for the multi-bit crypto system, they based on the low Hemingway combination assumption. Such that if we have F and G they have a low Hemingway. R is just some uniformly random from the ring R. and we have a term of R, FR plus G. So our decisional problem is how do we distinguish between this term and the second term? We know that this is uniformly random. This is uniformly random with and bits, and this one is unique. This one is with half, and I mean R is uniformly random, but F and G they have a low Hamming weight. So we hope that the products of FR plus G will also pseudo-random or nearly uniform. We just have that. And the second problem is the such problem. So suppose that they give us a term R, FR plus G. How can we find F and G? So the security of the multiple bits cryptography system based on this Mersenne combination assumption. And in this paper, they also prove that the cryptography system is semantically secure under this assumption. So how to prove that? So the first hint, we should remember that semantic security will be implied indistinguishable. I mean, it's indistinguishable in the sense as computational indistinguishable, and also computational indistinguishable also imply the semantic security. So to prove that this system is semantically secure, we will prove that this is computational indistinguishable. There are some definition for this notation. So suppose we have two samples, x equal to Sn, y equal to Yn. So two samples is just a sequence of probability distribution. We say that two is similar and polynomial indistinguishable. So that possible we have, and they did not like x will be nearly equal to y if for every probability polynomial time algorithm d, and for any negligible function. Negligible function, normally they will, in the paper they use the original form like the polynomial of based on the parameter n over 2 to the power of some security parameter, but actually we can consider it's like some negligible function. So we compute the probability that we can use the algorithm D to solve x, and then we compute the probability that we use the algorithm D to solve y, such that dx equal to 1, dy equal to 1, and then the difference in the probability is negligible. So we say that two examples x and y are computational indistinguishable. And they also define the pseudo-random. Like an assembler is pseudo-random if it's a polynomial indistinguishable from some uniform assembler UN. UN is just like a uniformly random for some random variable with n bits, and this bit is uniformly random from 0 and 1. And in here we say polynomial indistinguishable and computational indistinguishable, just the same meaning. They have some property of this notation. So if x and y are indistinguishable, then y and x also indistinguishable. The statistical indistinguishable. I have some grammar mistake here. If we have a statistical indistinguishable, we can imply the computational indistinguishable. So to prove that statistical indistinguishable, we need to compute the statistical distance, and then the statistical distance up to assembler is very small. Okay. The third property is suppose that we have x equal to y. Here I will use equal for the for the role of indistinguishable. So if we have x equal to y and y equal to z, then we have x equal to z. That means x and z are also indistinguishable. The fourth property is so simple that x and y are indistinguishable, and then we have some function, like some computational function f. So we will have fx and fy also indistinguishable. We will need this kind of property for our group. So we want to prove that this cryptography system is semantic secure. So first we need to compute. So remember that C1, C2 is the outputs of encryption process. This is TERF plus G belong to the public key. We want to prove that if suppose that we have two objects. The first object is RT C1 C2 and the second object is a sequence of four random variables. We want to prove that we cannot distinguish between two objects. So this proof is very easy. So first, based on the Mersenne combinational assumption, the Mersenne combinational assumption say that suppose we have R, we have T, we cannot distinguish this type with a uniformly random type. So based on this assumption, we have the first inequality. Next, we apply the fourth property such that if x and y are indistinguishable, so fx and fy also indistinguishable. So we compute again, and then we have this. Okay, because from R and T we can control AR plus B1 and AT plus B2. If we have R and R prime, then we can control this one. So this one is a product of RT and a product of RT and a product of R and R prime for some polynomial functions, for some function, some computational function. So apply this property and we have that the delta D will be very small. We apply, and also we also see that because the Mersenne combination assumption, we see that this one is uniformly random, this one uniformly random, this term is uniformly random. So if we ignore this one and this one, so we will have this one, the indistinguishability of this one and this one is also very small. So we have, this is based on the assumption of Mersenne. And then because we have this one, we apply the triangle inequality, and then we have this one. So that means that so then we done. The proof is done. So that means we say that the cryptography system is semantically secure. So we have a quiz interview about the history of the cryptography system. On May 2017, they proposed this system. From June 2017, they have a first latent attack from Benedet's Curly Zero Nakaset that I introduced in the beginning. From November 2017, the proof of author, they proposed the improved version of this cryptography system so that they can use to encrypt a multiple of bits, and then they can again the attack, the latest attack from Benedict and the other author. On December 2017, another group of authors they proposed the miss in the middle attack. And from September 2019, Divesh and Sibinis, they produce.
Let's say this.
Okay. They also propose another latest aspect using the same. I mean, very similar with the proposal by Benedict, but in this case, they propose a quantum triple L, and they use the advantage of quantum triple L to obtain the better efficiency in their algorithm. So the Mersenne Cryptography system is very new. The idea is very simple, and because we also work with integer, so the computational in this cryptography system is very efficient. But however, we also curious about their security, because for the ratio assumption and for the combination assumption, we still need a lot of returns into this assumption to understand more. And for the second proposal of Aggarwal, the multi-bit version, currently they don't have any attack for this version. I mean they have, but they just use the same attack that they implement on for the single bit, and with but however, we need more analysis on this version. Okay, I think I finished my presentation. Do you have any questions so far?
No, just thank you. Thank you, Tran.